Okay. Okay. This is going to be our last week of instruction. Next week we will have NSEM. You perhaps know it's, I think, July 6th. I will let you know the plan as during mid-sem we will take it in 2 sessions, and I will let you know the schedule. Okay, I think it's morning, 9 o'clock, so 9 to 10:30 one group, 10:30 to 12 another group. But of course it's not complete 90 minutes, something we are yet to finalize. Okay. But the format will be more or less the same as the mid-sem. Complexity-wise, I would say pattern-wise, and number of questions-wise, all this.
So in final grading, what will be the weightage of mid-sem, end-sem, and short?
We'll decide. Let us aggregate all the things and then we will see whichever comes good. What about the syllabus? This also I should mention. I would say the emphasis is on the post-mid-sem part, because these are new topics, and although I say that the emphasis is on post-mid-sem part, the pre-mid-sem part consists of certain things that you must not forget. That consists of variables, assignments, declarations, and what is that? Conditions, loops. No program you can write without these constructs, right? So in that sense, the syllabus is the entire thing. And I would say whatever is covered before the mid-sem was basically the basics or fundamentals. Okay. You should not forget this. If you forget this and do not take care of, revising those constructs, you cannot anyway write programs of more complicated post-mid-sem flavors. Okay, so that's the idea. But the topics covered after the mid-sem test will be the priority. Okay, most of the questions will be based upon these concepts. Okay, so that's one thing. Anyway, I will send you a more detailed email regarding the logistics and other issues. Maybe by Friday or so I will do it. Okay, so let us start today's topic. I would say this is the last topic that is included in your NSEM syllabus. Tomorrow, maybe I will talk about a little bit extra things, because this is a part of the syllabus. But because this is a smaller semester, smaller than usual semester, so we could not cover these things in detail. So tomorrow I will just give you an idea of the basic data structures like stacks and queues. Okay. With the understanding that this will not be part of your
Stack and queue will be. So stack and queue will be not present in our NSEM, no?
Yeah, it will not be part of your NSEM syllabus. But since this is part of the official syllabus, I will just give you a very brief idea what these data structures are and how they can be used in a variety of problems, for solving a variety of problems.
Sir, won't we do file IO?
Huh?
Won't we do file IO?
BTech? Yeah, please.
Sir, won't we do file IO?
File input and output.
There are many things. File IO, when we will do? In fact, if you look at any book, you will see that this file scanf, fscanf, fprintf, they are like normal scanf and printf. Okay, so you can learn it from books and other I would say online or offline stuff. Okay, we will not have time to cover this. It seems that I have got something like around 30 hours of class, whereas the normal semester typically runs for nearly 40 hours. So we have to discard certain things from the syllabus. Anyway, file IO is covered in a lot in PDS labs. Yes, I think PDS labs are more suited for giving you exposure to file IO. Yeah, that's another way of doing it. But anyway, we have to discard some parts of the syllabus. Another very important thing that we could not cover is something like number representation. Anyway, we have to accept this in this curtailed semester. Anyway, so let us talk about a new topic, which is today's topic. So let me share my screen. Which one? This one. Yes, so you can see my screen, right? It seems so. Okay, so this is some important thing that I will talk about today, although this does not immediately involve any C syntax or introduction of new C syntax. But the sorting algorithms are very, very important in computer science and in other situations too. Okay. So what I will do today is that I will typically focus on an array of integers. Let us say a 0 through n minus 1. Okay, it can be any other thing, but anyway, array of integers. So I want to rearrange the elements of A such that this following condition holds. A0 is less than equal to A1, A1 is less than equal to A2, A2 less than equal to A3, and so on until I have an minus 1. So this problem of converting an array A, which is arbitrarily ordered, to this what is called the sorted order, this problem is called sorting A. And of course, there is some order less than equal to here. So it is typically called in the ascending or non-decreasing or increasing maybe order. So I can similarly think of a dual problem where I sort in the reverse order. A0 greater than equal to A1 greater than equal to A2 and so on up to an minus 1. So this is called sorting in the descending or decreasing or non-ascending or non-increasing order. Okay. Of course, if the elements of A are distinct from one another, then all these less than equal to signs are essentially less than, and here all these greater than equal to signs are greater than. Okay, but in general, we should be ready to accept duplicate elements appearing in the input array A And if so, I should have this less than equal to rather than strictly less than. Okay. Anyway, whatever it is, this is the basic problem of sorting. And it is one of the most fundamental problems in computer science elsewhere too. I will talk about, let's say, 4 algorithms. Broadly, they are classified in 2 types. One is called iterative algorithms. The second one may be called recursive algorithms. For here, I have several algorithms: bubble sort, insertion sort, selection sort, and maybe also something like merge sort. Sorry. Heap sort. And in recursive things, most common sorting algorithms are called merge sort and quick sort. There are many other variants. Today, for the rest of the class, I will look at implementation and working of bubble sort, insertion sort, merge sort, and quick sort. Okay. Heap sort is a little bit complicated because it requires a data structure called heap. Yeah, any question?
So these are the 4 that we'll have in our syllabus.
These are the things you will have in your syllabus, but anyway, we can tell you a sorting algorithm and ask you to sort according to that algorithm.
Okay.
These are some things which are important, you should know. Not only from the perspective of your MSEM test, but from the viewpoint of learning and algorithm design also. So these are very important algorithms. Okay. Important and well-known algorithms. Maybe I start with bubble sort. Okay. So it works essentially like this. You have an array of integers. Okay, one thing in I must mention, that is that although we will typically sort things like this, integer arrays, but sorting is actually a more general problem. For example, I may also sort an array like B, okay, but then sort with respect to some field. Maybe I want to sort a list of student structures with respect to their CGPA, or with respect to their roll number, or maybe both, or maybe roll number, or maybe say with respect to CGPA and age, both. So first we will look at students having the same CGPA, and if there are ties, 2 students having the same CGPA 9.01, then the person whose age is smaller will come earlier. Okay, from this kind of, I would say, compound sorting criteria can also be used in order to sort arrays. Okay, so sort with respect to some field or fields even. So appropriate sorting criteria should be provided with respect to some appropriate sorting criteria. Okay, but that essentially implies you are talking about more about the sorting criterion and other things. I would, for simplicity, concentrate only on integer arrays because my motivation is to tell you the algorithms rather than this other paraphernalia. Okay. Okay, so I will concentrate on this only. So what happens is this. I will start with this and I will compare this with this. If I see that they are out of order, I will swap them. And if I see that this is already smaller than or smaller than equal to this one, then I will do nothing. I will go here. Then I will compare this with this. If I see they are out of order, that is, this is greater than this, then I will swap. So I will keep on swapping things as and when necessary until eventually I reach the last two elements and conditionally swap them if they are not in order. Okay. So compare consecutive elements and if not in order, swap. Okay. So if I make an entire pass through this array, what will be the effect of comparing all the elements followed by conditional swapping? What will be the final effect?
Sir, the largest element will come at
Oh.
n-1th index.
So after this largest element will be relocated to its rightful position. This is where it should belong, and by doing a sequence of conditional swaps after comparing consecutive elements, I have achieved this. I could push the largest element to the last position where actually it belongs. Fine. So it's something like bubbling the largest element back to the back of the array, to the last position of the array. Once I am done with this, I have now a slightly reduced problem. Because this largest element is in the correct position. Okay. Therefore, I do not need to worry about this element anymore. So it now suffices if I can sort the first n-1 elements. And I make a similar iterative bubbling process in order to bring the second largest element to the second last position. Once this is done, this largest element is in its correct position. After the second iteration is done, the second largest element is also in proper position. Then the problem is sorting the remaining n-2 elements. Okay. This keeps on going until only one element remains in the array, and a one element array is always sorted. So I will have the largest element, second largest, then third largest, then fourth largest, then fifth largest, blah blah blah, n-1 is largest, and then when only one element this I would say the size of the array starting from n to n-1 to n-2, it eventually goes to 1. I am done. Happy or not? So this is the so-called bubble sort algorithm. I will write a code for this.
Sir,
Mhm.
sir, could we do it like this? Like we swap the consecutive elements, and then we run like for all phases we run to the entire array, and in the last phase we check if the if there is any swap, basically like if there is any one swap, then we set a flag that it has been swapped.
No, that is fine. There are many ways of, I would say, improving the performance of this, but this is the basic algorithm. Okay.
Okay.
It is fine that if you are unable to swap in some iteration, then you know it's already in order.
Yeah, exactly. Yes.
You may quit. Yeah, that's true. That's true. Okay. So what I will do, I will first show you an animation. It should be there. Let me see. Yes, bubble. Yes. Okay. Make it big. So let's see. This is the array. So 70 and 67. I will first compare. And I see they are not in order, so I will swap 67 and 70. Then I will compare 70 and 15. They are not in order. So I once again swap 15 with 70. Done. Okay. Then I compare 70 with 94. They are now actually in order, so I will not make any swap. Instead, I will go to next. Okay. So 70, 94, no need to swap. Then I go to here. Now there is a need for swap. 92 and 94 will be swapped. So this, then I will compare 94 with 7. Again, they are out of order, so I will swap 94 and 95. That is fine, they are in order. So I will proceed further. 95, 52, they are not in order, so I will make a swap. Then this is once again a case of swap. Finally, this is the case of swap. Okay. So after this iteration, this of the outer loop, of course, there is an inner loop which keeps on comparing consecutive elements. But once the first iteration of the outer loop is over, the largest element has gone to the correct position. Okay. Then 94 should come here. This is the next element, and that I will do once again by bubbling, but avoiding this because it is already in the correct position. Yes, no, no, yes, no, yes, yes, yes. Okay, so after the second iteration of the outer loop, 94 has reached its correct position. This keeps on going. Yes, swapping needed, not needed, 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 needed. So 92 has now gone to the correct position, the third largest element. Okay. No swap, swap, no swap, swap, swap. Sorry, the previous one was not okay. This is not no swap. This is the case of swap. Okay. So 91 has now come. So this keeps on going. Okay. Let's see. 70 has come. Then 67 will come. 52 will come here. 23. This is fine. Then I am left with only one element array. I do not have to worry about this. It is already sorted. Okay. So this is how bubble sort works. Fine. I hope the algorithm is clear. Then I will go and write a code for this. So I will write all 4 algorithms here. Maybe I will use some random arrays. Okay. Okay, now that file IO is covered, maybe I just, as a passing remark, tell you something. What kind of argument main may take? You already know this, both the types. If you have to pass something to your main function, you have to pass it this way. Of course, the names argc and argv you can change, but it's one of the common names. Argument count, argument values. Okay. This is an integer argument. What is this character star argv this? What kind of data structure is it? You should already know it.
It's an array of pointers.
Array of pointers.
Okay. And how many pointers are there? This can be obtained from argc. So if it is 3, there are 3 pointers. And in fact, whatever C does, as far as I remember or know, if argc is 3, this argv0 will be your first argument, argv1 will be your second argument, argv2 will be your third argument. And you should not access beyond that, but as far as I know, argv3 will be the null pointer. So see, the compiler ensures that this is the null pointer. Okay. So that is another, I would say, kind of null termination. Okay.
Sir?
Sir,
main will be the first function to be invoked. Like it will be invoked by the program itself.
Who calls it? Yes.
Yeah. Sir.
Who calls it? Yes. We'll see. We'll see. So first of all, let me write the standard things. N will be the size of the array, and I will use 2 dynamic arrays, and I will also okay. So let me compile this. It will make some, yeah, I have not used any and b, that's why this unused variable warning is coming. Anyway, I will soon use it. Okay. So the question is, I can pass 1 or more values via this. Okay, so I have 5, 6 ABC and within quotes DEF. Then what I will do, I will just show you. If I run it this way, I equal to 0, I less than argument count plus I, printf, these are character arrays, right? So %s, new line, maybe say, I would say argv %d is equal to this, but I make it within quotes. I, argv, I. Okay. I, argv, I within quotes. Let us see. Okay, you see. The first argument is actually this. ./a.out or whatever way you run it. Second argument is, which is at argv1, it is 5, whatever I have said. Third one is 6, this is this 6. ABC, this is ABC. And the final argument is DEF within quotes. So this is DEF. Okay, so I hope now you understand how main receives its, arguments. Is it fine?
So, but what if we use an ID? Like if we use an ID, it directly runs the program, right?
But if you use?
Sir, IDE.
IDE, no, of course you can supply command line arguments.
Okay.
I think it should be possible. Of course, it depends on the IDE, but it should be possible. Supplying some, this 5, 6, A, B, C, D, E, F, these are called command line arguments. Let me just write it down. These are called command line arguments. Okay.
We will be having command line argument in our syllabus for NSEM as well. We will be having this command line argument. Will we have questions on command line arguments in our NSEM?
Look, if you think that everything you learn today, tomorrow, day after tomorrow is part of your NSEM, then I am not going to answer. Okay. So I'm teaching you something, just remember whatever you can. Okay. So don't ask whichever is in NSEM, whichever is not in NSEM. Okay. Anyway.
Sir, I have a confusion in the
till now we did not use these parameters in the main function.
Yeah,
so like suppose if we don't give, then how does it make a difference?
Difference of what from what?
So by giving these parameters, when we run the when we run the main function, we can give parameters from there only. That is the difference, right?
Yes, yes. So you just know how it can be done. Okay, that's it. Don't worry too much about
okay, then RC is the number of arguments it gets.
Yes, and that includes this first one. Okay, don't forget this. That includes this first one. But anyway, this is just a C syntax. Don't worry too much about it.
So we don't have to mention argc, right? It will be taken automatically. Like if we just enter the arguments, you don't have to mention argc.
Your shell will count how many arguments are there, and it will appropriately populate this argc. Yeah, that's true.
Yeah. Also, if we use spaces, we have to use double quotes, right? Like if you want to include spaces in our strings, we have to use double quotes. Otherwise,
double quotes. Some quoting you have to do.
Otherwise, they'll be counted as different arguments.
Otherwise, they are different arguments. Yes.
Okay.
Yes.
Sir, what if we want to include the double quotes as the part of the string in that case? Is there any method to do that?
Unmatched quote. So I cannot quote it by this. This is getting a little bit inconvenient. So what I will do, A, B or 5, A, B, C. Cannot I use this? No. Syntax may be something different. A double. Okay, there may be some way of doing it.
Okay. Means if you want to enter space separated string, then we have to enclose it in double quotes, right?
Yeah, that is true. But if you want to use quote as a character, this double quote as a character inside this string, I think this should be the escape sequence. But anyway, it's not. It's not working anyway. Anyway, we will see later. If this, there must be a way to do it. Yeah, other than backslash, what shall I use? I don't know. Anyway, forget it for the moment. Okay, so what I will use, I will not simply print
Hello,
this.
sir.
Yeah.
Sir, I understand the values the strings that we are entering, how are they getting assigned to RB without using any argument
This is
or
what this window is doing. You do not need to worry about this. Okay, it is the duty of this window. Whatever is running here, it will automatically convert that thing to this form. Okay, you don't need to worry about it.
so it's because of we have written those int argc and character pointers.
Yeah, I wanted to communicate with the external world, not just communicating between inside the function, inside the program, passing some values to some functions, getting some returned values. All these things are happening inside the program. But this program, when I run it, it also has a communication mechanism with the external world. And this is the input for the program. And this is the output of the program. Okay. In fact, if you say exit 0, exit 1, exit 2, whatever you say, this program which is running here, the shell, the so-called shell, that will receive this value, exit status. Okay. And there is a way to catch that status and do some certain things. And the shell may actually tell whether, looking at this exit status, it can say whether this is normal termination, abnormal termination, or whatever. Okay. Anyway, let's not worry too much about this. I only just mentioned this can be done. What I will do if, or I can write it this.
Sir, I have another doubt.
Tell.
Sir, these names are no way specific, right?
No,
These
any
are,
names you can use. Any name.
yes, these are standards.
Yeah, you can say AC, AV, any other name.
Yes, sir. Okay, thank you.
But people, this argc RFP people use this is a very common name, argument count and argument values. Okay.
Yes,
Sir,
sir.
argument values should it start with ./a.out?
Whatever you say. I can actually specify something. Instead of this, if I say this entire thing, starting from /a.out, then it will tell you this entire thing. So this is a part of the argument actually, the first one. Okay.
Okay.
Okay. So whatever you write there, that will go here. Okay. So argument count, if it is just 1, then I will randomly get some value of n, maybe just 10. Otherwise, I am actually trying to make sense of argv1. Otherwise, let's say just 10. If I do not specify any value, but argv1 is what? What kind of data set?
Address. It is a pointer to a character array.
It is a pointer to a character array, whereas n is an integer. So there is a built-in utility, argument to integer. This is perhaps defined in stdlib.h. Okay. A to I argv1, otherwise it is 10. A to I is argument to int. And anyway, let's not worry too much about the C syntaxes because we are essentially deviating from the original goal of looking at sorting algorithms. Okay, so what I will do after I get the value of n, I will create an array capable of storing n integers and another b. Okay. Then maybe for I less than n plus plus I will simply set bi, let's say rand percent 100. Okay, so now let me do one thing. Print array b. N. So let me write a function for this. Anything, any name you can give. Int hit I for I equal to 0, I less than n plus plus I printf percent maybe 2d ai and write a new line after this. Okay, so print array b of size n. Okay, so this is the array. Now whatever I say, that will be the array length. And if I do not say anything, it will take as 10. I can say 100 here. I will have a 100 element array, something like that. So this is a nice way of using this argc, argv kind of stuff. Okay, so now what I will do, first I will look at bubble sort. Okay, after I sort, the array is essentially, I would say, the original array is destroyed. So I will always make a copy from, I will not destroy the array B. I will make a copy of B to A. Then I will run bubble sort A n and then print array A n. Okay, so let me write the bubble sort function. Okay, so I need two loops. The outer loop runs from which one? N minus 1, and it will end at okay. Initially, I can go as far as n minus 1, and if I have a single element array, there is nothing to be done. So up to this point, so I equal to 1, this is the last thing. I equal to n minus 1, this is the first thing. Fine or not? Is this fine? In the first iteration, I will go up to n minus 1. Next iteration, n minus 2. And finally, when there is any, I would say, possibility of swap, this I is 1. Okay.
Okay, sir.
Okay. And then for j equal to 0, j will not be equal to I. Because if it is equal to I, then I and I plus 1 will be compared. So that is not our intention. J less than I plus plus j. If now we make a comparison of a j with a j plus 1, if they are out of order, I need another integer. Temporary integer, I need to swap it. P equal to AI.
So, can we like put this condition like j less than I
like I minus 1, because when I is at the last number, that is I is 1, then j is 0 and will run only once, so it will
Only
not
once,
have any
yes.
swapping because
Let it run only once. So what is the problem?
okay, sir.
Okay. The last thing is when I is 1, there is still a possibility of this and this getting swapped. Only when I becomes 0, then there is actually no comparison made. And so what is the question?
So actually I was saying that j will be at 0 and it will just enter the loop once, so will there be any swapping?
Will there be any?
So like when I is 1 and the condition is j less than 1, so j less than I, which means that j will only go into the loop once. So
Yes.
there will only be one element left.
No, I am comparing j with j plus 1. So a0 and a1 I am comparing.
Okay, sir.
Okay. Yeah.
Yes.
Okay. Okay. So that's it. A fairly straightforward code.
Sir?
If they're out of order, that's it.
Sir, t is equal to a j plus 1.
Huh?
Sir, t is
Oh, sorry.
I-
No, that's a mistake. That's a mistake. AJ, I will swap, not AI AJ. Yes. I am swapping AJ with AJ plus 1, not AI with AJ. AJ equal to T equal to AJ, AJ equal to AJ plus 1, AJ plus 1. Yeah, that's all. Yeah. So, okay, so instead of writing this, I will just say bubble sort, and let us see how it works. Oops, I didn't want so much. So this is sorted, right? One, next element is 12. 12 must be, yeah, this is 12. One, next element is 15, 16, 25. Anyway, so this is a straightforward algorithm. Yes or no?
Yes, sir.
Okay. Okay, so I don't know. This is the most favorite sorting algorithm for students in general. Anyway, I will also look at some other things. Okay. The second algorithm that I will talk about is called insertion sort. Okay. This works as follows. Suppose that this part of the array is already sorted. And then I look at this element. This may be already in the sorted order. If not, what I have to do is that I will find the correct position of this element in this sorted part of the array. If it fits somewhere here, I will bring it here and relocate the rest of these things to this. Happy or not? This is the one basic step of insertions.
So can you please repeat once again?
Okay. Maybe I will demonstrate this by a picture. This kind of thing. This is insertion, right? Okay. Suppose that this is the array to sort. So a single element array 97 is always sorted. Then I look at 52 and I would like to see where exactly it belongs before. Okay, let's see. 52. 97 is already sorted. 52, I see it belongs here. So 97 is relocated, 52 comes here. Then I look at 5. I keep on looking this position, where 5 actually belongs. Okay. Yes, I see that 5 is less than 52. So I will relocate 52 and 97. Okay. 97 comes here, 52 comes here, then 5 goes here. Then I look at 40. First I compare with 5. 40 is bigger, so I move forward. Bigger, so I move forward. Compare with 52. Now this is smaller, so I insert 42 before 52, but for that I actually require a space, empty space. So that can be obtained by relocating each of these remaining elements by one position. Okay, and so on. 28, it's too big. Yes, this is the correct thing. So 97 will come here, 52 will come here, 40 will come here, 28 will eventually fill this vacant position. 97, 52, 40, and 28. 50, no, it's big, bigger than 28, bigger than 40, bigger than 50. So I will relocate 97 here, 52 here, and eventually 50 will go here. Okay, then 38, still bigger, now smaller, relocate, 38. 14, bigger, now this is smaller. So 40 will eventually go here, but for that I have to relocate all the things. 97, 52, 50, 40, 38, 28. Now an empty space is created for 14. It will go here. 99. No, no, no. Bigger, 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 bigger. So it will stay here. Finally, if I look at 18, bigger, bigger than 14, smaller than 18. So I have to relocate everything. 99, 97, 52, 50, 40, 38, 28, and eventually 18 goes to the empty location. Of course, nothing is empty. It's conceptually empty. Okay. So this is one version of the so-called insertion sort algorithm. It is called insertion sort because during every iteration of the outer loop, you are picking one element and try to insert it before where the list is already sorted. So it's a kind of sorted insertion. Is it clear now?
Yes, sir.
Okay, right? Okay. Actually, this is the version which people often not prefer for a reason. Let me not highlight too much for the moment. What people do is they use this. Maybe I start with the same algorithm, same array, 5, 14, 18, 28. Then 38, 40, 50. Maybe that's good enough. 52, 97, 99. Okay. So 5. Let us. Oh, I see. It's already a sorted array. Stop. Start. Okay. No, this is not the thing I wanted to. Anyway, forget it. Maybe I'll go to the next page. 97, 52, 540. 97, 52, 5, 40. 28, 50, 38. 28, 50, 38. 14, 99, 15. Okay, so this is, forget this, 52. As long as, okay, I can start searching for the insertion position of 52 from this position, but it is a more common approach to start searching from this position. Is 52 bigger than 97? No. So then what I will do, I will put 97 here. Okay. And then I will see whether 52 belongs here. In this case, yes. So 52 comes here. Then 5. I look at 5. 5 is smaller than 97, so it will go earlier. So 97 will be put here. Even smaller than 52, so 52 will come here, and then 5 will stay here. Then I look at 40. 40 is smaller than 97, so 97 will come here. Smaller than 40 is smaller than 52, so 52 will come here. But 40 is larger than 5, so I will put 40 here. Okay, so maybe another iteration. Up to 40 it is done, so 28. 28 smaller, so 97 will come here. 28 smaller than 52, so 52 will come here. 28 smaller than 40, so 40 will come here. 20 is not smaller, 28 is not smaller than 5. So 28 will come here and 5, and so on. Okay. This variant I will write, and in fact you will find this variant in the slides which I will upload today. Okay. I can do it, right?
Sir, is there any benefit of using one variant over other, or it depends on array?
It's actually yes. If the array is already sorted or very nearly sorted, then this variant is actually better. Why?
Lesser comparisons.
Less number of comparisons. If it is already sorted, then you start comparing here, 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 and eventually find it should belong here. But meanwhile, you have wasted so many comparisons. Okay. But if you do this way, then by making a single comparison, you are done. You know I am in the correct position. So, okay. So this is the reason sometimes people prefer this variant, but other variant is also okay. Anyway, so what I will do now, I will write the code for this insertion sort. Insertion sort, once again copy. Okay. Int I, j, t. Now I will start to relocate on onward, right? Okay. I do not need to start from an effort of relocating 97 because a one element array is already sorted. So I start from I equal to 1. Okay. And the element that I am wanting to relocate is nothing but the ith element of A. Okay, I will remember this. Now, okay. maybe I minus 1. Which one should I do? Maybe I start from j equal to I. When j is greater than 0, what I will do? If t is less than, if t is greater than aj minus 1, I will break. So first I check whether ai is greater than ai minus 1. If so, I break. Okay. Otherwise, I make j minus minus. At the end of the loop, I simply say aj equal to t.
Sir?
Yeah.
Sorry, in this code, won't the element at jth index initially will be overwritten and that information will be lost?
That's what I have stored it. First of all, I am storing that ai in t. Right. After storing that, I am. Oh, I see. I didn't make this relocation, right?
Yes, sir. Means.
I didn't make this relocation. So, okay. aj equal to aj minus 1. Okay. Okay, if I find that t is already greater than aj minus 1, I simply break. Otherwise, I will copy aj minus 1 to aj, then go to check the next smaller value of j. Okay. So that's a mistake. Sorry. This is fine, right?
Sir, j should be equal to I minus 1 because it is starting before one element of I.
No. Again, I look at this. Look at this. So indices are 0, 1, 2, 3, 4, 5. Now I am storing in t the value 50. Clear, right?
Okay, sir.
Is not greater than 97. So 97 will come here. Right? aj is aj minus 1. So that effectively, of course, 97 is still written here, but effectively it makes a blank space, conceptually. Okay. Then I compare this 50 with 52. 50 is still smaller, therefore this 52 will come here. Then I see 50 is larger than 40, and this is now an empty space. Conceptually, of course, 52 is written still there. Then I break the loop and simply put this 50 in position j. Right? H equal to t.
Yes, sir.
Okay. And this may happen entirely down the line, but I will never. There is a second way. Second way, this loop can break. If this break is not explicitly executed anytime, then eventually j becomes 0. In that case, I simply say a0 equal to t. Happy? Okay, so let us see. Yeah, there is no reason why it will not work. 30. Good. Okay. So this is how insertion sort works. Oops. It's already 4:14. Okay. So maybe let us have a 5 minutes break. Then I will talk about the more complicated recursive algorithms, merge sort and quick sort. Okay. So this algorithm is clear, right? Insertion sort.
Yes, sir.
Okay, starting from index I am comparing this T, which I want to insert, comparing with the previous one. If I see T is still larger, still smaller, then I will bring that previous element, the jth element, decrement j, and keep on searching. And so once we have found the correct position for inserting T, it's broken. Okay. So this is a fairly straightforward algorithm anyway. Merge sort and quick sort are slightly more complicated. So let us have a small break. Hello, I am back. Okay. Next algorithm that we are going to discuss. Okay, good. Is called merge sort. This was proposed, as far as I remember, by John von Neumann in mid-1950s. It's an interesting algorithm, and one of the first algorithms of type divide and conquer. So actually, although it's a divide and conquer, there are actually 3 stages: divide. So you are given a problem, you generate sub-instances of the same problem. Sub-instance 1, sub-instance 2, up to some sub-instance k. Then you solve the sub-instances recursively. And there is actually a third step, which is called the combine step, or you may call solve plus combine together as conquer. Combine the solutions of the sub-instances to a solution of the given instance. So this is the basic principle behind any divide and conquer algorithm, and merge sort is one such thing, one such algorithm. So here what I do, the divide step is, this is my array A of size n, let's say. Divide step is just cut it into two pieces. This is the left half. This is the right half. Okay. So now we want to sort the sub-instances, sort this to this, and then sort this to this. So there are 2 sub-instances created. So recursively sort left half, recursively sort right half, then, so these are recursion. So after this recursive calls return, so recursive calls can never make mistakes. So after they return, this is a sorted array. And this is also a sorted array. Okay. And of course, you should have somewhere recursion should stop somewhere. So it may stop when n is 1 or 2. Or maybe just 1. Okay. So n is 1 or n is 0. In 0 case, actually, we will not have. Anyway. So a 1 element array does not require any sorting. So this is the base, induction basis, recursion basis. Then what I have to do, I have to somehow combine this sorted list with this sorted list and make a single sorted list. So merge. So this combine step here is called the merging step. Okay. So this is the basic divide and conquer idea. Here the divide process is trivial. Just split the input array into two equal halves. Definitely, if the size of the array is odd, then one will get n by 2 floor, other will get n by 2 ceiling, something like that. Apart from that, it's just splitting the problem into equal halves. Recursively sort them. Recursion should stop when you reach n equal to 1. Okay. And when the recursions return, this is sorted. The second recursion returns, this is sorted. Then you have to somehow merge this sorted list with this sorted list to a sorted list of size n. Okay. So let us see how this can be done. First of all, I use an animation to demonstrate this merge. Okay. Okay. So it's a recursive algorithm. So some call stack is good. How many elements are there? 8 elements are there. So here all splitting will be even. 4, 4, then 2, 2. Okay. So let's see. So I start merge sort 0 to 7. Entire array. Split it in two halves. 0 to 3, 4 to 7. So first I make a recursive call, sort this. Okay. Then this is of size 4. Once again I make a split 80, 27 and 54, 46. So I make the first call first, 80, 27. Finally, this is once again I have not reached this base case, n equal to 1. So I will once again split it in two parts, 1, 1. So merge sort 0, 0. Now this is something which does not require any effort of sorting. A single element array is always sorted. Okay. So this call returns merge sort 0, 0. Second call will be merge sort 1, 1. Okay. Once again a single element array is sorted. So this will also return. So this is a sorted array, one element array. This is another sorted one element array. At this step, I have to merge this with this. Okay. For this, I will use this external array. I will use two pointers. I will find out which one is smaller. 27 is smaller, so I will copy 27 here. Then I see that 80, this is exhausted, so 80 will be copied here. And then what I will do, I copy back this here and this here. So that is the merging step, but it will be clearer when I look at merging larger instances. Here also, let's see, 54, single element array, nothing to be done. 46, single element array, nothing to be done. Then I will have to merge 54 with 46. 46 is again smaller, so I will copy here. 54 is smaller, so I will copy here. Then I will copy back. 46, 54. Okay, so this first recursive call now gives me a, no, not yet, it's a sorted array. So I have this. This is a sorted array, this is a sorted array, I have to merge them. Okay, so 27 is smaller, come here. Then 46 is smaller, so 46 will come here. Then 54 is smaller, so 54 will come here. Finally 80, this is the only element left, so this is this. And then I will move, copy back this element here, 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 here. And that's the end of the first recursive call. At the end of the first recursive call, the first half of the array is sorted. Then the recursive call is made, merge sort 4 to 7. Okay. And this will proceed exactly as before. 6685. Then I will merge this 538 with 6685. 5 smaller will come, 38 smaller, then 6685 it will go. So now I have two recursive calls returning. So this part is sorted, this part is also sorted, and I have to merge this to 4 element sorted arrays into a single one. So once again I use 2 pointers. 5 will come here. 27, 38 I compare, so 27 will come here. 46, 38 I compare, so 38 will come here. Then 46, 66 I compare, so 46 will come here. Then 54, 66, this is smaller, so 54 will come here. 66, 80, 66 is smaller, so 66 will come here. 80 is smaller, so 80 will come here, and then there is only one element left in the second array, 85. And then I copy back. 5, 27, 38, 46, 54, 66, 80, 85. Okay, so that is eventually sorted. Happy?
Yes.
In fact, okay. In fact, this is the same sorting algorithm that I have used in the last class to sort or to merge to sorted lists. One containing even integers, the other containing odd integers. Okay, this is the same strategy.
This is the best sorting like algorithm till date.
This question let us not raise for the moment. There is a lot of theory behind this. Merge sort is theoretically a good algorithm, but practically a better algorithm is quicksort. Okay, but why? Please don't ask me. We do not have enough machinery to illustrate or even give you the slightest idea why it is so. Okay, that requires a lot of mathematics, some amount of machinery, which we cannot develop. Okay, so if I need to write a code for this bubble merge sort, 5 lines, okay. Merge sort, copy B to A instead of insertion sort, merge sort, AN print. Okay, so I have to write this code. Void merge sort A okay, so if n is less than equal to 1, return. Don't do anything. A 1 element array or a 0 element array has nothing to be there is nothing to be done for a 1 element or a 0 element array. Otherwise, what I will do, I will take n by 2 elements, make a recursive call. In order to avoid floor and ceiling calculation errors, if this is n by 2, it is n minus n by 2. Of course, if n is even, then n by 2 and n minus n by 2 are the same. Otherwise, they are not. Okay. So when these calls return, the portion of A starting from index 0 to n by 2 minus 1, that is sorted, and also n by 2 to n minus 1, that is also another sorted array. Happy? Now I have to merge these things. Okay, merging in place is a difficult thing. So what I will do, I will create.
Sir, we are calling merge sort with the same pointer. So will that work? Means I am confused. We shouldn't change the second statement to a plus n by 2.
Yes, sir.
Yes. The standard mistake. A plus n by 2, of course. Otherwise, we are sorting the same array. A plus n by 2. Yeah, we have to give a shift. Sorry. Yes. Okay. And that auxiliary array that I have used here, this, I have to create space for this. malloc n star size of int okay. And maybe what I will do, I will use a set of indices. Left start, left end, right start, right end. I will run over the left half, J will run over the right half, K will be for writing to B. Okay. What is left start? 0. Left n, that will be n by 2 minus 1, right? The size of this left half is n by 2. So n by 2 minus
Yes,
1.
sir.
Okay. Then what will be right start? This will be just
N
one
by
more.
2.
Yeah, n by 2 just. Or I can say LE plus 1. Immediately after the left half ends, right starts. And right end will be just n minus 1. N minus 1. Okay, so I will scan the left half in the index I. So it will be left start. J will be right start. Okay. Now I will make a loop while I less than equal to left end and K should be 0. K is for writing to B and J less than equal to J or less than equal to right end. Okay. Both the sub arrays will not exhaust together. But this OR means, if I do AND means neither the left half nor the right half is exhausted. But I have to continue merging when at least one of these two halves contains some element. Okay. So there are several cases. If I is greater than LE, that means the left half is exhausted. So I will, without making any comparison, copy from A, J, right, J runs over the right half and increment this J after this copy. Okay. Else, if the right half is exhausted, J is greater than right end, then I will copy from the ith index. Okay. Otherwise, both halves have some elements. I will compare AI with AJ. If that is the case, then BK will get the value from AI and I will be incremented after that. And finally, BK will get the value AJ and J will be implemented. Happy or not? In all these cases, after this copy is made, I will increment K. Happy?
Yes, sir.
No mistakes, right, this time? A plus plus I plus plus I plus plus A plus plus. Yeah, I do not see a mistake. Okay. Then I have to copy back. The entire n element thing. Equal to 0 through, or I can use k. Whatever, it doesn't matter. I can use I can use k, whatever. A equal to bi. And then as a courtesy, I free the element with the array b, which is just used to help the merging process. Okay. Happy? I think this is fine. Left start is 0, right start is left end plus 1, left end is n by 2 minus 1, right end is n minus 1, I equal to left start, j equal to right start, and k is 0. Yeah, it seems fine. Let us see. Okay. Okay, fine. Of course, you can embed this part in a function, but anyway, it's okay. Happy?
Yes, sir.
Oh. Then this, any question?
No, sir.
Okay. Okay. So then I have only one more sorting algorithm that I want to cover. It is this. Where is my writing pad? Yes. That is called quicksort. It was designed by Charles Anthony Richard Hoare, C-A-R Hoare, a British scientist, computer scientist, come mathematician, whatever you call him. This is a nice algorithm. It is once again an example of divide, conquer, combine. So this time divide step is more complicated. Conquer is just a pair of recursive calls. In this example, actually, in the case of quicksort, this is trivial. Essentially, nothing to be done in the combine stage. So in merge sort, divide is trivial, right? You simply cut the array into two splices, two sub-arrays. But the merging process, which is the combination process, that is somewhat complicated. Quicksort does the complicated work before making the recursive calls, and after the recursive calls return, there is nothing left to be done. You can simply return. Okay, so the idea goes like this. So let's say this is the array we want to sort. Once again, if n, the size of the array, is less than or equal to 1, there is nothing to be done, so you can simply return. Otherwise, we choose some element in this array as what is called the pivot. Okay. So in this example, in this class at least, I will take A0 as the pivot. Okay. Then what I will do, I will make a pass through this entire array. I will locate the elements smaller than this pivot. I will classify them. I will also find those elements that are larger than the pivot. And I also have the pivot. For simplicity, let us assume that the elements are distinct from one another. Otherwise, you will have to find out how many elements are equal to the pivot. So that's another way of doing it. Okay. Then, if these elements are something like this, up to this, and these elements are something like this. Okay, so this is less than array, this is the greater than array, and then I have this. Then, if I just write the less than array, this is followed by the pivot, this is followed by the greater than array. And then if I make a recursive call on this less than part and a second recursive call on this greater than part, then after this recursive call, this part is sorted and pivot is in the correct position. This is larger than all elements, smaller than it. And after the second recursive call, this is also in the sorted order. So it's a sorted array followed by the next possible value for pivot, followed by the larger values. This is also sorted. So there is nothing left to be done. Okay, so this is the basic idea of quicksort. Okay. So let us once again see the animation. Okay. So pivot, something I choose. There are various ways of choosing the pivot. Some people choose the first element, some people choose the last element, some people choose a random element. And there are many other good strategies for choosing pivot. I will just choose 86 as the pivot. Okay. So quicksort 09. 86 is chosen as the pivot, so it's copied here. Then I see. Okay, I see. Maybe I will tell you the easier version first. Ah, yes, this is the easier version. Then I will look at this. More complicated. Okay. So this is the array I want to sort. 57 is the pivot. This is the space for pivot. 57. Then I make a pass through this entire array. Whichever are smaller, I will keep it in this array. Whichever is larger, I will keep it in this array. Okay. 35 is smaller, so I copy here. 90 is larger, I copy to the second array. 9 is smaller, 44 is smaller, 36 is smaller, 48 is smaller, 80 is larger, 64 and 65 are larger. So I use two external arrays for this dividing process. And in the case of quicksort, this divide process is called partition. Of course, with respect to the pivot. Okay. Okay, so now if I copy this part, followed by this, the pivot goes to the correct position. 35, 9, 54, 44, 36, 48. So this part is not sorted. we made currently up until now I have made any attempt to sort this. I have just figured out which one is smaller, which one is larger. Then 57 will go here. So 57 has now occupied the correct position. Then 90, 80, 64, 65. Okay. 57 is in place. I am not going to change its position anytime after this partition. Okay. Then I make a recursive call on this and a recursive call on this. First recursive call between 0, 1, 2, 3, 4. So quick sort 0, 4. Okay. So once again I choose 35 as the pivot. Make a partition. 9 is smaller, 44 is larger, 36 is larger, 48 is larger. And if I once again copy back, first 9, then 35, 44, 36, 48. Then in addition to this 57, this 35 is also in place. Right. Now I make a recursive call on this and this. 9. 0 to 0, one element array, nothing to be done, return. Then 44, 36, 48. So 44 I will again choose as pivot. 36 smaller, 48 larger, 36, 44, 48. Now again I see that 44 is in the correct place. I have to make two recursive calls on this and this, but they are one element array, so they will immediately return. Okay. So when the first recursive call returns, this part is sorted. And then 57 is already in the right position. So what is left is to sort the remaining part, 19, 90, 80, 64, 65. Okay. So once again, I choose 90 as the pivot. 80 is smaller, 64 smaller, 65 smaller. So I first copy 80, 64, 65, then 90, and then of course this is empty. So the second recursive call will not be done. So 80, okay, chosen as pivot, 64, 65. So once again, if I copy 64, 65, 80, there will be no second part. Okay. Then 64, 65, this array I have to sort. 64 is chosen as the pivot, 65 is larger. So I will copy this. This is currently empty. 65 will come here. This is the one element array. Nothing to be done. Eventually, everything is sorted. Happy or not?
Yes, sir.
Yes,
Oh,
sir.
okay. Okay. So what is good about quick sort is that we do not actually need these extra arrays. Okay. So maybe tomorrow I will just briefly tell you how this, without using any extra array, partitioning can be done. But today, for the sake of completeness, I will write the code for quick sort with extra arrays. Not a star a. Two arrays I will use, less than, greater than, and of course I have to use a few indices. I less than, greater than, and maybe I will use a pivot. Okay. Again, if n is less than equal to 1, there is nothing to be done, return. Okay. Then I choose pivot to be a 0. And I will copy from array A. Oh, first I have to give some memory to L and G. Okay. Maybe just size n minus 1 is also fine, but anyway. Greater than array will be n star size of int, pivot equal to this, L and G. These are the writing index in the two arrays. Okay. For I equal to 1, I less than n plus plus I equal to 0 is the pivot position. So if I see AI is less than equal to pivot, okay, then L plus plus will be AI, else R plus plus will be AI. And in all cases, I am doing I plus plus. Okay, so this is the partitioning stage. After this loop terminates, whatever the small l, lowercase l stores, that is the size of the capital L array. Whatever G stores is the size of the capital G array. Okay, so what I do, I again copy back I equal to 0, I less than L plus plus I equal to Li.
Hello. Sir, in this function, what is R? You did not declare. Sir, R, capital R.
This array I call capital L, this array I call capital R.
Sir, but you did not declare R, you declared G, I think.
Oh, I see. There is a mistake, right? Okay. Not left, right, less and greater. Okay. Not left, right. That is G. Now this is correct, right?
Yes, sir.
Okay. So first copy the less than part, 0 to L minus 1. Then a L is nothing but pivot. And then for I equal to 0, not right, greater G plus plus I, A, L plus 1 plus I equal to GI. This is correct, right? 0 to L minus 1 copied from less than array, then the Lth index, that is pivot, and then L plus 1 through L plus 1 plus G minus 1. This is copied from the greater than array. Okay. So this entire process is partitioning. Then you recursively make the call A size L. How many elements do I skip? Those L elements plus 1 for pivot, and its size is G. Happy? And after this recurse, there is nothing to be done except that as a courtesy, I will free L and free G.
L minus 1 should be pivot, and for I equal to 0, I less than L minus 1, the loop should run. Here L minus 1 equal to pivot, because for the last element you enter when the pivot is entering an array, then you see a for A of I less than equal to pivot. So pivot element will also get inserted in L.
No, maybe you are telling something. Can anybody understand? The voice is coming very, I would say, disturbed. Maybe my minor mistake somewhere. Yeah, I don't know. Can anybody understand what he said?
Sir, if I am not wrong, I guess he's telling that in the for loop we are taking from 0 to L. So he was taking, I think he was telling to take to L minus 1, but I don't think that's a mistake.
Sir, what I was telling was that we are comparing A of I less than equal to pivot. So pivot will also get inserted in L now.
I am starting from I equal to 1.
Yes. Oh, okay, sir.
Okay. Yeah. Okay. Let's see. Okay. So let me finish this main. Quick sort this one, quick sort print array AN. Okay, fine. Okay, it seems okay. Okay, so this is already past 5. If you just give me some 5 minutes, I can talk about that thing. Okay, let me complete it. Okay, so in the early animation or even in this code, what I have done, I have used 2 extra arrays. But anyway, since the total number of elements in these 2 arrays will be n minus 1, so I can also actually allocate a single array of size n minus 1 and write the less than part from the beginning of that array and greater than part from the end of that array. That is also fine. But anyway, what is important to note here is that I actually do not need any extra array for that matter in order to do this partition thing. So the idea is something like that. Now the pivot will be 86. Okay. Pivot will be 86, a bit too large for this. Okay. Left and right. So I am not very sure what kind of version is written here. Let's see. Pivot is 86. Okay. So what I will essentially do, as long as I will see things smaller than the pivot, I will keep on advancing this L pointer. Okay. 23 is smaller, 8 is smaller. So, oh. Okay, so this algorithm is perhaps not the one that is given in the slides. Anyway, so the idea is that L will keep on incrementing. 86, 39 is smaller, 37 is smaller. And why am I stopping here? I should come here. Anyway, this algorithm I do not remember what I have implemented. Okay, so I can tell you this thing. That does not worry too much about this algorithm I forgot. There are actually millions of ways in which partitioning can be done. What we can do is something like this. I will use a pointer here I will use another pointer j here, and so long as ai may be less than pivot, I will increment I, and while aj is greater than, of course I have to use equality sign somewhere, minus j. Okay, so what will happen here? This is smaller than pivot, this is smaller than pivot, this is smaller than pivot, this is smaller than pivot. Maybe suppose I have stopped here. Okay, so instead of from here, this is smaller than pivot, smaller than pivot, smaller than pivot, smaller than pivot. This is, let's say, greater than equal to pivot. I have stopped here. I has stopped here. J finds greater than pivot, greater than pivot, greater than pivot, and maybe something less than pivot. And then J stops here. Okay. So this part is fine, less than pivot, less than pivot, less than pivot, less than pivot. This part is also fine, greater than, greater than, greater than. Now I is pointing to, or is an index to a location, which is storing a value greater than equal to P, and this is storing a value which is less than P. Then what shall I do?
Swap.
I simply swap AI with S. After I do this, this becomes less than P, this becomes greater than equal to P, and then once again I can move the forward march. I can once again increase as long as it finds less than equal to less than P values, and J can once again move backward as long as it finds greater than equal to P values. And once again, if it finds some kind of mismatch, AI will be swapped with AJ, and then once again the forward march of I and the backward march of J will continue. Okay, and this will happen as long as I is less than equal to J or something like that. When the two pointers I and J cross or become at the same position at that point, I should stop. It should be written a little bit carefully, but this is one partitioning algorithm.
So what is the starting means initial value of I means it is the index of element
0 and n minus
1. Okay, sir.
Or you can make 1 and n minus 1, and then you will relocate this 0th element. So there are many other details for this online partitioning or in-place partitioning. The idea is this is very important, is that I do not need any extra array for doing this partition. Whereas in the case of merge sort, merging without using that extra array may be a bit too costly. But what is meant by costly and all that stuff, this is not clear to you, and let it stay like that. We do not have time to cover this so-called big O notation and all that stuff. Okay, but this is one of the basic ideas, and there are other ways of partitioning. As long as this is smaller than P, to stop when you find something greater than equal to P, and greater than equal to P, greater than equal to when you find something less than P. And then at that point of time, you check that there is not a crossover of I and J. That's also possible. If not, simply swap, then a then a less than P value come here, and a greater than equal to P value will come here, and then once again I can restart the march of I rightward and the march of J leftward until either they both point to wrong values or they cross each other. Okay, so that's basically the idea, inline or in place partitioning. And it's because of this actually in practice, this quick sort happens to be very, very, I would say, efficient. Okay, so this is practically efficient. although it's although merge sort is actually theoretically efficient. Okay, anyway, what is meant by efficient and all the stuff we will not have opportunity to look at. Okay, so okay. Okay, so let me stop here. If you have any queries, please let me know.
Sir, I had one query in strings and strings portion. Sir, in the slides, it is written that if you allocate a string constant to a string pointer, then what happens is that space in memory is created for this string constant, and the starting address is assigned to that pointer. But that is not happening in my compiler actually. For example, means char star s is equal to Aditya. So means this is not compiling, but in slides it is written that this will work fine.
Which compiler are you using?
Sir, code blocks.
Oh. No, this kind of thing works here. In my machine it works. This should work. Technically there is no problem. In fact, if I define something like this, character star s equal to Aditya, it should work. This should work. In fact, based upon this, a question is set in your short test. There is only one small thing there. This is a constant string. Okay. So there was actually a problem in that code. Again, in my compiler, in other compilers it may work. So this is a constant string. So A, D, I, T, Y, whatever this string is, it stays in read-only memory. So you cannot later change it. You cannot simply say S0 equal to B. This is not allowed. But the question that we said was based on such a setting. But anyway, technically it is fine. Conceptually it is okay. But in practice this will make a problem because this is read-only memory. Maybe because of the security issues and all that.
You were talking about that question in which there was a string like 463 and then some number, and we have to print on the after.
Yes, exactly. So maybe because of security reasons and all that stuff, these compilers do not allow that. Because it will not allow you to write in a constant part of that memory. And I think this is the major issue is the security issue. Otherwise, different types of attacks are possible. I don't know. Anyway. There are many things compilers allow with some warning and all that stuff. Like this is getS. If you compile with GCC compiler, it will say this is dangerous. Do not use getS. Use fgetS instead. Anyway, let's not worry too much about this. But this kind of construct should work.
Okay, sir. Means theoretically it is right. It may be something in the compiler.
Yeah. So whether or not it's read-only and you cannot change it, but this construct is fine. But that should not be a problem.
Okay, sir.
Okay. So any other question? Okay, so how many of you are there? 50. Okay, then see you tomorrow. We will do something.
Thank you, sir.
Oh, bye.
Thank you, sir.
Okay, thanks for joining. Bye.